Okay, so thank you very much and welcome back to this SID seminar. So today we are very happy to have Lorenzo Dello Schiavo, who is telling us about Liouville Quantum Gravity in even dimension. So please, Lorenzo, go ahead.
Well, first of all, good morning, everybody. Thank you very much for the kind introduction. And thank you very much to all of you organizers, and especially to Matteo for the invitation. It's a great pleasure to be, even if virtually, at ISP. And I should say a few words about the title, which is not corresponding to the one that was done in the abstract. This is sort of the short title. The title in the abstract is precisely the title of this paper, which is a bit too long to fit the slide. I should point out that everything I'm going to present is joint work with Ronan Herry at Centre Henri Lebesgue of Rennes and with Eva Kopfer and Theo Sturm in Bonn. Okay, and this is based on a paper that appeared relatively recently. This is 2024. And also, let me spend a few words to thank funding institutions, the Austrian Science Fund, which funded my position until a while ago, and then the DFG, the Deutsche Forschungsgesellschaft, through this special program SPP 2265. Okay, and now to the mathematics of it. Well, the important bit, which is sort of the goal of the talk, is to convince you not only that Liouville quantum gravity is an interesting topic in its own, but also that one can go sort of beyond what was the common understanding until a few years ago, which is two-dimensional, and explore the realm of Liouville quantum gravity in every even dimension. Okay, even will be important, but the goal is to go beyond two. And of course, I should start by recalling what happens in dimension two. Now, in 2D, the main object of study is a type of very rough random Riemannian geometry on a surface with a given Riemannian geometry assigned. So the setting is a Riemann surface, sorry, which I will denote by sigma G. G is always the Riemannian metric, with scalar curvature Rg. I will describe first the mathematical object and then explain the physical meaning, because of course the theory stems from a highly relevant theory in physics. So, I mean, this is a mathematical translation of physically relevant concepts. And let me start with the deterministic case. So the sort of the end goal is to study a random version of the following action functional, which is the deterministic Liouville action functional. This is a functional on conformal metrics with respect to G. So all metrics that can be obtained from G by applying a conformal weight e to the power 2h, where for the moment h is a function, and eventually it will be something more singular. In particular, it will be a distribution. How does the Liouville action functional look like? Well, it's a functional of this form up to, say, normalization. It has one energy term. You can imagine that if you disregard everything else and you integrate this term by parts, you will get a Laplacian, so you will get a Hamiltonian of a free particle. It has a curvature term. Here, theta, capital theta, is just a real valued constant. So it has a curvature term from the scalar curvature of the Riemann surface. And then it has this exponential term in the field, in H, which is called the matter field. Now, why is this functional important? Well, mathematically speaking, first of all, because this is a nice functional that is conformally invariant, at least for some choice of a parameter, in particular for theta equal gamma over 2, where gamma is this gamma here, which is the most important parameter in the business. And conformal invariant here means that if you change the reference metric G in a conformal way, then you get a nice formula. Now, the second point is that extrema of this functional, so by doing a bit of calculus of variations, extrema of this functional solve the Liouville equation. And therefore, they provide solutions to the Riemann uniformization problem. In a sense, what you want to do is move your surface to a diffeomorphic surface where you're changing the metric in such a way to solve Riemann uniformization. In the case of domains in the complex plane rather than surfaces, the Name of the game is to map conformally your favorite simply connected open domain to the disk, which is exactly what the Riemannian uniformization problem proposes to do. And now the solution is a change of metric, which is a conformal change of metric. And a conformal change of metric is given by solving this equation, where this operator is nothing but the Laplace-Beltrami operator in the conformally changed metric, while delta zero is the Laplace-Beltrami operator of the reference metric. So for instance, on the disk. And here what you can write explicitly is the curvature for the conformally changed metric, which gives you the solution to the problem. And the curvature will be a constant curvature of this form. So negative constant curvature in the case of surfaces. Now, okay, so essentially what we want to do here is, instead of considering the deterministic functional, considering the functional acting on distributions. So instead of taking a conformal change by a function, we take a conformal change by h in d prime. And this is called the quantum Liouville action. Why is this important? Well, this has been introduced by Polyakov in a couple of papers in the 80s. There is one for the bosonic setting, which is the one I'm going to talk about. And there's one for the fermionic setting, which I don't have the time to explore. But in the bosonic case, the important bit is that this action functional is a good model for the following physical phenomenon. The quantization, so we talk about functionals and distributions, of a bosonic string. Bosonic string means we have this energy term for, say, the free particle, coupled with a matter field, which is this Liouville field in the deterministic case, and the 2D gravity. And this is the effect of gravity. And gravity is, as usual, modeled by scalar curvature, so in the 2D case at least. And this model is in the conformal gauge, meaning that since the functional is conformally invariant, at least for some choice of parameters, the functional behaves well with respect to conformal transformations. And physically speaking, conformal transformations are just a change of coordinate from the point of view of the observer. So you want your model not to depend on where your observer lies. Is there a question?
I think mine's fine. Okay.
I'm sorry, I cannot hear you well. Are there questions? No, okay. So as I said, this is a model and for the bosonic string in a conformal gauge. And conformal invariance or covariance, so the conformal transformation for which we can identify exactly how the transformation happens, will play a central role throughout the rest of the talk, because we want the theory to have this feature. And so whenever you see a green box in the following box like this, it means that we are discussing the conformal covariance or invariance properties of the objects involved. Now, this again goes back to the 80s, but there's been a lot of mathematical theory. And most of the mathematical theory, at least in the beginning, was necessary simply to make sense of the objects much before exploring their properties. Because of the following mathematically serious issues, which are that, first of all, okay, we have a term that is coupled with curvature. This is just curvature times a function. And we know how to make sense of, say, a distribution applied to curvature. This would be just the duality pairing. We can say the curvature is a function and apply a distribution. But then we have more serious problems. What is the gradient of a distribution? We know it's again a distribution, but it's not clear already what is the modulus of a distribution, and the least what is the square of that. Okay, so the energy term we need to make sense of in a suitable way. And also, more importantly and more difficultly, we need to make sense of this exponential term of a matter field. And this is again mathematically challenging because we do not know what the exponential of a distribution is. Eventually, once we've made sense of the action functional, the very end goal is to make sense of a functional in order to define the associated Gibbs measure. And this will be a Gibbs measure on the space of distributions over our surface. Okay, this is why we're interested in minimizers of this functional in the deterministic case. And now let me recall what is known and has mathematically been developed in the past maybe 20, 25 years in the case of two-dimensional Liouville quantum gravity. The rest of the talk will be essentially devoted to make sense of these objects, also in the case of dimension higher than 2. But let me start with dimension 2. So again, we need to make sense of a field. We want a random field of distribution. And it has been understood already early on that the best way to study this object is to consider as the field Gaussian free field. Gaussian free field is sort of the log-correlated Gaussian field, at least in dimension 2. Now, the correlation structure depends on the dimension. I'm going to point out this in the following. Here, I list contributors to the theory. I should immediately point out that there's many more that do not appear on the slides that also made extremely important contributions, but the community grew exponentially in the last few years, and it's extremely large by now. So please do not be offended if your name does not appear immediately. Now, there's been a lot of contributions to the study of Gaussian free fields because of their universality. They satisfy certain universality properties. There are limits of a large variety of models in the discrete. The next object we need to make sense of is the exponential. For the exponential, this has been done in different stages. Maybe the first result in this direction is the definition of Gaussian multiplicative chaos by Kahan, and then we can apply Kahan's abstract result to the case at hand. So for the Gaussian free field on, say, the disk or a Riemann surface. I'm going to comment in the following about geometric aspects. For the moment, I'm just stating what is known in a sort of general two-dimensional setting. Now, what one should do is, instead of trying to make sense of the object pointwise, make sense of the integral as a whole. Okay, this is reasonable because in the end of the day, we're talking about distributions, so they're not pointwise defined. And this is the main obstacle, sort of the key problem. We do not know how to make sense of a function computed at a point when we are taking h to be a distribution. What we can make sense of is the whole integral, and it turns out that even if h is a distribution, this is a measure, a nice measure, like the standard definition. Okay, and this is called the Liouville quantum gravity measure. There's maybe a more recent construction, which is fairly abstract, but nonetheless it is helpful, and this is the one we are using in the paper, and it's a construction by Sharmov, which is more general than the one originally produced by Kahan. And then we need to make sense of the energy term, and the energy term in dimension 2 is nice because it is a Dirichlet form. So it is something like integral of gradient square with respect to the reference volume. And therefore, it has an associated stochastic process. The stochastic process, it's interesting in its own right, and it is called the Liouville Brownian motion. It is the Brownian motion of this random geometry. So in essence, what we're doing is taking a fixed geometry, a reference geometry, which is the one of sigma g, constructing a change of the geometry, which is random because it depends on the field. And what we have here is the volume of this geometry and the Brownian motion of this geometry. This has been introduced by Vergata, and then it's been studied by Gerban-Roth and Waches by means of Dirichlet forms theory. I should also point out, because this is extremely important and there's a huge part of the theory which I'm not going to touch, that this is only one half of a picture. So we have described a random surface with a random metric and a random measure, but in fact, the metric induces a random distance, and there is an interplay between the distance and the volume measure, similar to the one that appears in classical smooth Riemannian geometry. And this metric part of a picture, so far we dealt with the measure part of a picture, but the metric part of a picture has intimate connections with the Brownian map and many other objects. And I think this will be also explored in the second talk of today's section. So now putting all things together, what one can do in 2D is completely satisfactory in the sense that there is a full description of the theory. We can make sense of its functional. We can describe very explicitly the associated Gibbs measure, Polyakov-Liouville Gibbs measure. And this has been done first on the disk by Duplantier, Sheffield, Miller, Sheffield, then on the sphere, and finally by Guillermo, Rhodes, and Vargas on surfaces of genus G greater or equal to 2. These three constructions, although they are sort of similar in spirit because the goal is the same, are different from a technical viewpoint because of the topology of these objects and their geometry. In a sense that on the disk one needs to take care of a boundary. It's clearly important. On the sphere, it turns out that one needs to do the so-called vertex insertion, which is in this respect a kind of regularization procedure that allows to create singularities in the sphere, in this case 3 singular points, where your reference metric diverges in such a way that you can account for the complement having negative scalar curvature, which is a feature that you want in the theory, for purposes that I'm not gonna go into at the moment. And this is the case for surfaces of genus larger or equal to 2, when you already know, again by uniformization, that there exists a unique hyperbolic metric of constant curvature -1 on these surfaces. Okay? In dimension higher than 2, the picture is much more complicated. There has been up to now, before our work, partial results. Maybe 2 important results are the one by Baptiste-Saclay, who deals with spheres in every even dimension, essentially by reporting everything to the case of Euclidean spaces by using stereographic projections of a sphere. And then there is a heuristics by Levy and Oz. This is physics heuristics, which turns out to, let's say, not to be precisely on point, because what we do is identify some topological obstructions that were not covered in this heuristic. So this is a kind of this is a kind of dream that we want to be able to construct these objects on every possible 4 or 6-dimensional manifolds, but it turns out that it's not possible, mathematically speaking. Now, other questions so far? I should say, please feel free to interrupt me. It seems not. Then let me move to the case of higher dimension. And again, what we want to do is make sense of these 3 objects. The main point is that we want to keep conformal properties alive, because again, from a physical point of view, we want our theory not to depend on our coordinate system. And it turns out that in higher dimension, this is more difficult for the following reason, that if you, for instance, look at the energy term, you integrate per part, you take the Laplacian or the Laplace-Beltrami operator of your surface. In dimension 2, this is conformally invariant. Okay, so if you change the metric, the Laplacian of the new metric will have a factor in front, which is a function given by your conformal change, times the old Laplacian. This is the Liouville problem that I showed before. In higher dimension, this is no longer true, which means that we need to replace the Laplacian with something else. We need to replace the Gaussian field with some other objects. And these are the objects that I'm going to describe now. So the first ones are what we call copolyharmonic operators. These are the right generalization of the Laplacian for our purposes. And now here, let me talk about the setting. The setting is that Mg is an n-dimensional closed Riemannian manifold. And closed means compact, boundaryless. Okay, so you already see that we are no longer addressing cases like the disk, for instance. It will be extremely important throughout the following that the dimension is even. I will point out where this comes into play. But it is extremely important. Everything I'm going to say is for even dimensional manifolds. Of course, the most interesting case is maybe dimension 4, but one can do more general results for manifolds of higher dimension. Again, throughout the talk, G prime will be a conformally equivalent metric to G with conformal factor phi, and our factor is smooth here. When we change coordinate, we do so in a smooth way. Now, PG is the right generalization of the Laplace-Beltrami operator. It is what we call the copolyharmonic operator, and it is the right generalization because it is conformally covariant, in a sense that it satisfies the following formula. If we change the metric G to G prime, then we get the same operator of G times e to the minus n phi. Remember, for the Laplacian, we had something like Laplace-Beltrami of G prime equal e to the minus 2 phi Laplacian G. Okay, this was our previous conformal covariance formula. Now this n here, sorry, this 2 here is of course the dimension. And it's important to note that, in a sense, as a consequence of this fact, these operators are not second order differential operators. They are higher order differential operators. So the first step when the dimension comes into play is we need even dimension in order for this operator to be to have integer order of differentiation. Okay. Now PG is in fact part of a scale of operators, and this is a well-studied scale of operators which are called Gram, Jenne, Mason, Sparling operators. They are again differential operators for k different than n, so other operators in the scale are in fact operators on differential forms, two differential forms of different order. Okay, but in the sort of what is called the critical case, which is the NN case, these are differential operators which can be regarded as differential operators on functions. I'm unfortunately unable to go into the construction of these operators because the construction is extremely sophisticated. I have maybe some slides in an appendix if you are interested in the construction. But the important bit is these operators exist, and in a sense they are the right generalization of the Laplace-Beltrami operator for our purposes because of this conformal covariance formula.
So I'm not an expert, but I mean, listen, in 4D, they are differential operators of which order? Like
I'm going to give you more details and examples right away. So in dimension 2, the copolyharmonic operator is exactly up to sign the Laplace-Beltrami operator. For our purposes, it's important that these operators are positive. In dimension 4, these operators are fairly explicit. They are called Paneitz operator, and they can be written explicitly as a perturbation of the Laplacian square. So Laplacian applies 2 times. This is a fourth order differential operator. In general, the construction could be done in the following way, at least heuristically. Take the right power of the Laplacian, which depends on dimension, and add some terms to make the operator conformally covariant. It turns out that this remainder that you're adding is of lower order. So these operators are a lower order correction of the appropriate power of the negative Laplace-Beltrami operator, obtained in such a way to give you this conformal covariance formula. Okay? This is why they are treatable. There are other explicit expressions as long as you have sufficient knowledge of a Riemannian metric and you are in a nice setting. For instance, on Einstein manifolds, you could give explicit expressions, or at least more explicit expressions. They are, however, not easily treatable in a sense. Okay? For our purposes, it's just important that we have this formula. The definition will not be particularly relevant. Are there more questions? Okay, then what is the next object? The next object is the replacement of the scalar curvature. Scalar curvature is in 2D particularly important because it is what gives the description of gravity. Okay, And now the point is, again, we want an equivalent in higher dimension, which is conformally covariant in a suitable sense. We can find this equivalent, and this equivalent again comes from conformal geometry that's been studied long before for purposes of conformal geometry. And this is Branson's Q curvature, introduced by Branson in 1995 and then later studied by, for instance, Branson and Gover. Now, this curvature satisfies the following conformal covariance formula. Again, you take the same object for the metric G prime. You get the old one for the metric G by a conformal factor, which depends on your conformal change. And then you get, again, the same factor times PG of the conformal change of phi. Okay? Again, it is an explicit conformal change formula. Why can Branson's Q curvature be understood as the right generalization of the scalar curvature? Well, first of all, because it has nice invariance properties and sort of, it's not exactly a topological invariant, but at least goes in that direction. Why? Well, first of all, because if you define the total curvature, the total Q curvature, so you integrate the Q curvature on all of your manifold, this is a conformal invariant. But Gauss-Bonnet in dimension 2 curvature is in fact topological invariant, total curvature is a topological invariant. Here it's no longer true, it's just a conformal invariant. But still it encodes information about the topology, okay? Because, okay, in dimension 2, this is exactly what I said. It coincides up to scalar with, up to factor 1/2 with the scalar curvature. And therefore, the total Q curvature is just 2 pi times the Euler characteristic of your surface. But in higher dimension, what you can say is the curvature satisfies, the total curvature satisfies the following rigidity. If your total Q curvature is this multiple of Euler characteristics, then your manifold is conformally flat and vice versa. Again, in some dimensions, on some manifolds, you can give explicit expressions. Okay? This is particularly important, but let me stress that whenever I say conformally flat, conformal change, and so on, all of these properties are global. Okay? Conformal transformation means a global conformal transformation with a smooth conformal factor, and conformally flat means globally conformally flat. All right. This is the generalization that we were after for curvature. What we need now is to define generalization of the Gaussian free field. Now, this is a sort of standard fractional Gaussian field described with the right covariance operator. Okay? How to do this? Well, we need some properties of a copolyharmonic operators, which tell us why in the construction of the fields, they are the right generalization of a Laplacian. First of all, we want to be able to make smooth computations, not to deal with higher order Sobolev spaces and manifolds. And this is achieved by knowing that the operator is essentially self-adjoint, which simply means that it's completely determined by its action on smooth functions. Remember, we have no boundary, our manifold is compact, so there are no boundary conditions that we need to take care of. Okay? Their domain as closed operators is the Sobolev space of order n, which you can picture as essentially this image via the resolvent of a standard Laplace-Beltrami operator with the right power of L2. And this is the case because this operator is a lower order perturbation of minus delta G to the n over 2. And therefore, this lower order perturbation does not affect the domain as a set, but affects its norm. Okay? And secondly, this is the important bit, this operator vanishes on constants, and this is true only in even dimension. Okay? This is a serious restriction. In odd dimension already, you do not have this property. You have a zero order term, usually. Now that we have these two properties, we need a further one, which is for sort of the most important to define a covariance function. And this is what we call admissibility, which is to say that PG which vanishes on constant, vanishes only on constants, and is non-negative definite. This is a property of minus Laplacian, but in general is a property that we want for the resolvent of our operator to define a covariance kernel. If the operator is not positive, then it cannot define a covariance, because covariance must be positive on there. Okay, and also it must be non-degenerate in the sense that it must vanish only on functions. Let me point out for future purposes, just a bit of notation. Whenever you see a ring, this means that we consider grounded objects, so objects up to constant. Well, up to constant means up to some additive constants, which we are factoring out of the picture. In this case, this is the grounded Sobolev space, which is just a standard Sobolev space of the right order, having removed constant functions. Okay, with this assumption in mind, this operator has a kernel for its inverse, so it is invertible on grounded functions. This is the same for the Laplacian, that do not exist on a closed manifold non-trivial polyharmonic functions, as well as there do not exist non-trivial harmonic function. The only harmonic function is the constant function 1, and you can bootstrap this to show that there do not exist functions that are non-constant for which higher power of a Laplacian vanish. So the kernel of the operator is just constant functions, and once you factor out the kernel of PG, then this has an inverse, and the inverse is an integral operator which can be represented by an integral kernel Kg. Okay. Now, what we do is study fairly explicitly Kg and compare it to the kernel for the n/2 power of the Laplacian. Why? Because for the Laplacian we have much more information, and we need the same information for the copolyharmonic operator. What one can hope for is that these two integral kernels are very close. In fact, they're close in a very strong sense. In essence, how close they are does not even depend on how close we are to the diagonal of a manifold, because this kernel must diverge on the diagonal of a manifold. And what we see is that one can control explicitly the divergence of a kernel close to the diagonal, and this divergence is logarithmic, which is exactly the right generalization we need in order to have a log-correlated Gaussian field. And this log correlation is important because something with a rougher correlation would be too much of a distribution, and so we would not be able to define its exponential as Gaussian multiplicative chaos. And something with a more regular covariance function would be closer to being a pointwise defined functions. Okay. So the generalization here is of this logarithmic divergence along the diagonal, which gives the right covariance structure. Once we have the right covariance structure, what we can do is define a copolyharmonic Gaussian field, which is the centered Gaussian field with covariance given by the integral kernel of Kg, where for convenience, I always remove this constant here. Okay, this an is just a universal constant. It's something like 2 4 pi to the minus n/2 gamma of n/2. So it's really a universal constant. It only depends on dimension. Now, this field will be the equivalent in this business of the Gaussian free field. Okay. In particular, it is a log-correlated field. It is the log-correlated field defined with covariance given by the copolyharmonic operator. And for this reason, we can expect that it is the right conformally covariant object. We made all of this generalized construction to get conformal covariance. So let's explore how it works. Now, the main strategy to show that some object that is rough, like these fields of distribution, is conformally covariant, is to approximate it with conformally covariant more regular objects, for which the conformal covariance can be studied explicitly by essentially change of variable. Okay. For this, we need the following, that Pg is a compact perturbation of an operator we know more about, is minus Laplace Beltrami to the n/2. And in particular, this implies that Pg has discrete spectrum Therefore, we can find an orthonormal basis of eigenfunctions for this operator. And also, the eigenvalue, the corresponding eigenvalue, satisfy Weil's asymptotic, okay? Which means that nu j behaves in the following way as j diverges. It is essentially the growth at infinity of a sequence of eigenvalues of this operator. And now what we can do is define a suitable sequence of approximations, which are more regular, in terms of eigenvalues expansion. Now, in dimension 2, there's a lot of different ways in which one can regularize the Gaussian free field in such a way to obtain good approximations. One can do circle averages, spherical averages, one can do eigenfunction approximations as in this case here. But the point is that on a general surface, especially in dimension higher than 2, if you don't have sufficient structure, in dimension 2, maybe you have a complex structure, and this is of great help in doing, say, circle average approximation or approximations obtained by integration along contours. But in higher dimension, this simply goes away. Okay, so the easiest possible way is to do eigenfunction approximation. And it's also, in a sense, the most reasonable way. Now, eigenfunction approximation means exactly what it means for the free field in dimension 2. You take the eigenfunction, you rescale in the appropriate way by the eigenvalue, and then you multiply by some IID standard normal factors, these variables xi j. Only you truncate the series at some constant L. Okay? The expectation is that as L goes to infinity, this converges to the original field, because this is the eigenvalue expansion, the eigenfunction expansion of the field. Of course, the convergence must be dealt with in the appropriate spaces, in the sense that the limit H will be a distribution, because it is a log-correlated Gaussian field, so it has the same regularity of a Gaussian free field in dimension 2. And therefore, the appropriate distribution, the appropriate space of convergence is the negative grounded Sobolev space, where we don't have regularities of functions, but rather regularity of a distribution, or generally the space of distributions in the appropriate topology, the standard topology on the space of distributions. While here we need to regard these approximating fields as measures in order to make sense of a convergence. So we want to see a distribution also before taking the limit. The right distribution is the function HL times the volume. Now, let me show you only the conformal covariance formula, and then I'll ask if there are questions. Conformal covariance formula looks like this. Again, we are changing the metric by e to the 2 phi g. This is our metric g prime. And h prime is the field constructed with the copolyharmonic operator of the metric g prime. How does h prime relate to h? Well, in the way you expect, up to correction. In the way you expect means that, again, it varies with a factor e to the n phi, where phi is the conformal weight. But then you need to correct for the fact that the field is no longer grounded in the right way because the volume is changing. So remember, we are working in spaces that are grounded, so we want to factor out constants. But the orthogonal of constants as in terms of a norm depend on the metric. In particular, depends on the volume measure. Therefore, we need to address this change and make a new correction. And the new correction is essentially the grounding of a previous field multiplied by the new volume. And the grounding of a previous field just means that we compute the old field at the conformal factor. This is a distribution, so we need to regard this as a distribution pairing. Again, what we are just saying is we're decomposing our spaces of distributions, or our negative Sobolev spaces, into everything that is non-constant and constants. But in order to make this splitting conformally covariant, we need to adjust our fields by this factor. Are there questions? It seems not. Then let me move on. What we want to do now is define Gaussian multiplicative chaoses. So define the Liouville quantum gravity, the Liouville quantum gravity measures, the random measures associated to our random Riemannian geometry. And now the idea is, of course, we want to study the following as a measure. But already Kahan understood that this makes sense only if we apply a correction. And so we need to subtract the variance of the field. This is the only way in such that this object can hope to have a limit when we do reasonable approximations. What does here reasonable approximation means? Well, we need to regularize both the field and its covariance structure. And this can be done simultaneously in many different ways. What we want to do is find some regularization that satisfies, say, the abstract assumptions for the construction of Gaussian multiplicative chaoses, either those by Kahan or those by Shamov, and then apply as a black box Kahan or Shamov. We will do this with Shamov's results in such a way to obtain a limiting construction, which in fact will not depend on the chosen approximation. A nice way to do this on manifolds, where we don't have much structure to begin with to construct such regularizations, is to consider regularizing operator of integral forms in terms of radially decreasing Friedrichs modifiers. So we take small balls, we take a nascent delta function at the center of a ball of radius so small that is contained in the ball, and the ball is maybe contained in a chart in such a way that, at least morally, we do not need to bother about the fact that we are on a Riemannian manifold rather than on the Euclidean space. It is actually not so easy to verify that this satisfies Shamov's assumptions, but indeed it does. And what we need to do is, beyond regularizing the field, also regularizing the kernel and construct the following sequence of approximating Gaussian multiplicative chaoses, which are exactly those that you expect. And these are now nice smooth measures, okay, because these are smooth functions given with the eigenvalues, with the eigenvalue expansion, or with QL regularized expansion. Now, theorem, the limit of these measures exists. It exists in L1. This is a consequence of the abstract results by Shamov, and it is independent of the approximation. Again, the difficulty here is verifying Shamov's assumptions, and in particular, the uniform integrability condition on this family of measures, if you're familiar with Shamov's result. Now, again, let me describe the conformal covariance formula. This is a bit more involved. It requires some more notation. First of all, again, we need the grounding of a field, but also we need factors that account for how the conformal change intervenes in the change of the kernel, so kg. And this factor is what we denote by phi bar, and is this quantity. Essentially is twice the average of kg in one coordinate, and twice because kg is symmetric, so we account for both the first and the second coordinate of kg, and the grounding of the whole field, the whole kernel in both coordinates. And now that we have these quantities in mind, we can write explicitly the conformal covariance formula for the measures, which looks like this. Again, we have the measure for the reference metric. This is a random measure now, but again, it's expressed in terms of g, and what we're doing is computing the one in terms of g prime, times the following exponential factor. Exponential factor contains the grounding of a field, the conformal change factor, and the grounding of the kernels, of the covariance kernels. Okay, now we have almost all the objects in place. There is one more that we need, and it is to say we need to make sense of the energy. The energy means the term integral gradient squared. What we can do here is make sense of this term by replacing the gradient with the square root of pg. No? In dimension 2, at least on Euclidean spaces, one can picture the form as integration by parts of gradient squared to get the Laplacian. Here one can do the same, but with a square root of the Copolyharmonic operator. Of course, what changes is the domain of this function. This is the same as in dimension 2. The domain is a Sobolev space, yes, because in the end these are differential operators and we need to make derivatives. but it is Sobolev space of representatives of L2 functions with respect to our random measure. And this is the key point. This was already understood in dimension 2 by Gaban Rodenwagers when they constructed the Dirichlet form of Liouville Brownian motion. And this is just the higher dimensional generalization. It turns out that this form is a well-defined non-negative closed symmetric form on L2 of our random measure of our Gaussian multiplicative chaos. So of a Liouville quantum gravity measure of our Riemannian manifold. And this is true for every gamma in the usual range of parameters. I'm not going to discuss very much the parameters. I know that physically speaking, the parameters are extremely important, but let me say that there is no big change in how the understanding of the parameters varies in higher dimension, at least from the point of view of the construction. Now, there are nonetheless some key differences with respect to the two-dimensional case. The first difference is the following. In the two-dimensional case, this functional would be a Dirichlet form, okay? Which means that it comes with an associated stochastic process, namely Liouville Brownian motion. In higher dimension, this is no longer the case. It is no longer the case because this square root is not a gradient, and it has too high order as a differential operator. One could say, okay, let's replace this operator with the actual gradient. This would give us a Dirichlet form. Yes, and it would come with an associated stochastic process. But the point is that that construction would not be conformally invariant. So there is a sort of dichotomy in higher dimension higher than 2. Either you can keep Dirichlet, so being a Dirichlet form, or you can keep conformal covariance, but not both at the same time. In a sense, this suggests that Liouville Brownian motion should not exist. I will comment later on about this because there's been recent development in this direction in January this year. Now, a further point is that, again, this form can be used, as in the case of dimension 2, to define the sort of equivalent of a random Laplacian of a surface, and this will be the random copolyharmonic operator, okay? That is to say, the generator of this random form, which is essentially the one obtained by integration by parts of this guy. Are there questions? Seems not. Then let me move on finally to describe Polyakov-Liouville measure. Okay, this is the end goal. What we want to do is consider the Gibbs measure of this action functional, exponential of minus SGH. Of course, we do not have a reference measure because we know that there is no analog in infinite dimensions of the Lebesgue measure. So the only hope is to make sense of the exponential density together with the measure as a whole, okay? In fact, we can do this provided we replace all the right objects in the definition of a functional. Again, we have shown that the scalar curvature is replaced by Branson's Q curvature, that we can replace the energy by this guy, and we need to address the field. The field, of course, will be replaced by the Liouville quantum gravity measure. So in the end of the day, what we have is this new functional, which is the right way to interpret the functional on functions. So the first line shows what the functional would look like if h were a function, and the second one, what it actually does look like since h is a distribution. And we have constructed all of these objects, okay? We have this factor here that accounts for how we add constants, okay? Which in fact can be factored out. It is in fact factored out in most of work in 2 dimensions. Now, the idea to make sense rigorously of a measure is use Feynman's heuristics, which is the same as the heuristics for, say, the construction of a Wiener measure. We do a type of regularization procedure again. And it turns out that we can construct this measure. This is the Polyakov-Liouville measure in dimension higher than 2 even, But we can do so, and in particular, we can do so means that we can define a finite measure for specific choices of the parameters that now have into account some topological constraint. Because remember, the total Q curvature speaks about the conformal class of your manifold. In particular, it gives some, even if not global, but some information on the topology of your manifold. And this is important because, in a sense, these constraints that do not appear in dimension 2 are constraints on, in a very vague sense, the shape of the universe. Not every shape of the universe is admissible. This is also related to admissibility for the copolyharmonic operator. Not on every, say, 4-dimensional manifold you can do this construction. There are, in particular, some topological obstructions to this. Okay, and again, okay, you can give the definition and you can study conformal covariance. And the goal here is to understand what is called the conformal anomaly, which is just the right transformation factor, Zg. This again depends on phi, and this is the dependence on phi. This dependence on phi is fairly complicated, but there is every term that you expect. There is the energy of phi with appropriate constants in front. There is the height of phi, which is again the grounding of phi with respect to the new metric. And then there is a factor which depends on phi and the averaging on the kernel, integrated with respect to the curvature. Okay. This turns out to be the right conformal anomaly, such that when we shift our Polyakov Liouville measure with respect to the following shift, which is again sort of the right Cameron-Martin shift in our space of distributions, then we get a conformal covariance theorem. The conformal covariance theorem is rigid in the sense that it's true only for specific choices of the parameters, which mimic those that are familiar in dimension 2. And in this case, what one has is that these newly constructed measures satisfy exactly the conformal covariance formula that we were hoping for. When we change the metric G to G prime, we get a conformal anomaly explicit in this form, times the old measure shifted by this shift operator. Okay, this is sort of the end goal that we wanted to reach. Now, let me conclude with a quick recap of what I said by comparing the 2-dimensional case with the case of even dimension. Now, in dimension 2, the theory works on all Riemann surfaces with adjustments on the sphere and on the torus, because the sphere and the torus do not have constant sectional curvature -1, do not admit a metric with such constant sectional curvature. Instead, in higher dimension, the theory only works on admissible manifolds, because you want to construct covariance functions that have the properties of covariance functions, and this you can do only if your copolyharmonic operator is non-negative definite. Of course, this includes Riemann surfaces. It includes some closed Einstein manifolds with positive Ricci curvature, so not all closed Einstein manifolds, and many others, but importantly, not every manifold. So there are obstructions, and in particular, these obstructions are topological in nature, or related to the conformal class. Furthermore, the analog of a Laplace-Beltrami operator is the copolyharmonic operator, which has been studied before in this Graham, Jenne, Mason, Sparling scale of operators. The analog of scalar curvature is Branson's Q curvature. The analog of the Gaussian field is the copolyharmonic Gaussian field. The analog of the LQG measure, so the Gaussian multiplicative chaos of the Gaussian field, is the Gaussian multiplicative chaos of the copolyharmonic Gaussian field. And the construction is sort of standard. The difficulty is verifying the assumptions in abstract existence result. Now, in dimension 2, one can construct Liouville Brownian motion. In higher dimension, there is no conformally covariant Brownian motion, provided that you do the construction with Dirichlet form theory and you interpret conformal covariance in that sense. But there is a recent work by Bertacco and Nguyen where they do a different construction, giving a different interpretation of conformal covariance, which generalizes the conformal covariance of the Liouville Brownian motion in dimension 2. So it could be that the right way to go is find a more appropriate notion of conformal covariance for Markov processes that allows you to do the generalization, which does not come by choosing energy forms defined in terms of the Copolyharmonic operator. And finally, the end goal is achieved. One can construct the Polyakov-Liouville measure, and this is conformally covariant only for the right choice of the parameters, provided you satisfy the following condition. So the measure is finite, provided you satisfy the following condition, which again starts speaking about the topology, which is a feature only of dimension 4 and higher. And with this, I want to thank you very much for your attention, and I'm happy to take questions.
Thanks a lot for the nice seminar. Indeed. So if there are any questions, please please stand up virtually.
Since I'm not an expert, I'm not afraid of asking stupid questions. So, so in 2D, this is it's a measure for the metric, right? So you indeed have a quantum gravity. So in higher D, so the fluctuation of the metric is within some constrained subspace of possible admissible surfaces, or what's happening here?
This is a very natural question, but I must say from a metric point of view, on manifolds, there is absolutely no result. There are some results by Ewan Gwynn and co-authors on Euclidean spaces, where they construct the conformally covariant distance, which is fitting the picture. But these two pictures are skewed because they work on Euclidean spaces, where they can do reasonable approximation, and we work on closed manifolds, where no such approximation is available, and the case of Euclidean spaces is not covered. The expectation is that there should be a conformally covariant distance, which is the distance arising from the random geometry, but we have no serious idea how to actually construct it. So this part of the picture is completely open.
I see. Thank you very much.
Okay. So I think okay. So if there are no other questions, I think we can thank again our speaker. Then let's say that we take, I don't know, 10 minutes. Okay, so we resume in 11:40 or something, and we start again. Just perhaps let me only say something. So I want to advertise a nice workshop that we are organizing well, let me show the poster. Perhaps it's not sure if it is. Yes, okay. So there is this very nice workshop we are organizing at the Institute Pascal. So let me share the screen so you can see it. Okay. So this is the annual. Okay, you can see it here. So this is the annual workshop that, in a sense, is a bit of a summary of all the themes the topics we kind of discussed this year. So this is the current list of speakers. I hope it's the definitive one. And sorry, so it's the 25th of April at the Institute Pascal. I hope you can make it. Of course, there is it's all free, but you should come somehow register if you want to come. Okay, so let's break for like 8 minutes, and we resume in 11:40.